In this video, we are going to talk about forces, and I'm going to show you some few things about forces. Now, there's lots and lots of different kinds of forces out there, used for lots of different things, lots of different ways. A bunch of them connect together. And we're going to look at a few of the main ones today. Now, often when you start talking about forces, first of all, you kick into Newton's second law, F equals ma, and we look at how that works. And that's usually where our first specialized force really kicks in, because this one is typically net force, or the total force used in a situation. That's typically what you want to use for your F equals ma expression. Now, first of all, you want to then typically look at what is often called an applied force. And this is the force that is trying to move it. It could be gravity trying to be moving it. It could be somebody pushing on something. It can come from lots of different ways, but the applied force is what's trying to move it. And if that's the only force involved, then that is your net force. But there's often friction. Of course, friction tries to slow things down, where if there's friction in a situation, you need to subtract the friction from an applied force to give you your net force. If you're pushing with 10 and friction is 2, the net force would only be 8. Now, friction often comes from different places, but a really common force used to find friction is the Fn, or normal force, or natural force. And that's the force that comes from when there's two different surfaces. So this comes from between surfaces, and they're in contact with each other, and there is a contact, or almost like a pressure force between them. And this is often used to find friction. Not always, but it's really, really common for normal force to find friction. And that's why our formula to calculate friction is mu Fn, where mu is the coefficient of friction. Now, really, really, really common force used for tons of different stuff, including Fn, is the force of gravity. Now, of course, gravity can be used to try and move stuff, but it also can be used to actually find the normal force. It's really, really common for something sitting on a table, or like a book or a box, wherever you want. The force of gravity is pulling the object down onto the table. The table then pushes back up, which is the normal force, and that normal force is then used to find friction. So these things often link together. Gravity is often used to find Fn, or it can be used to find applied force, and sometimes that Fn is then used to find friction, and then these two are often used to find the net force. So there's lots of different forces out there, but they're often not just by themselves. They often end up leading to other things. Another really common force that often kicks in is tension. Sometimes we'll talk about tension. And this is just the force that's in a rope, or a cable, or some kind of like string type thing, whatever, being used to pull something or apply force to something. So that often kicks in as well, and can come from applied force. It can come from gravity. It can come from pretty much whatever's actually pulling on the object. So let's see if we can actually just take some of these forces and actually identify where they are in a situation. So here we have a really common forces type situation, and we got two masses, which happen to be fruit attached by a string or rope, whatever it is, with a pulley, one of them sitting on the surface. So let's just see where some of these actual forces exist. Now, net force, we're going to leave that alone right now. If we looked at some of the basic forces on this thing, well, two of the most basic forces acting on both these things is gravity. So both fruit have a force of gravity. Now, the force of gravity for these two fruit actually end up doing very different things. For the strawberry, the force of gravity is actually pushing it down onto the table. And because of that, the table is actually pushing back or straight up on the strawberry, which means the force of gravity of the strawberry is actually creating the Fn between the strawberry and the table. And that Fn could then be used to find the force of friction between the strawberry and the table. The orange obviously doesn't have any friction because it's not actually sitting on anything. So in that case, you get the force of gravity would find the Fn. The Fn could be used to find the friction for the strawberry. For the orange, it's different. The force of gravity isn't involved with an Fn or friction. The force of gravity is what's actually trying to move it. So this force of gravity is actually the applied force in the situation. So it's what's actually trying to move the system. And not only that, that force of gravity is also responsible for the tension in the string. If that orange wasn't there, there'd be no tension in the string whatsoever. So therefore, it's responsible for it. So again, different forces can lead to different things depending on where you look in the situation. Now, if we actually had all of these forces, the only one we haven't mentioned yet is good old net force. And if you would then take what's trying to move it, the applied force, and subtract the friction, those two would then give you your net force for the situation, which could then be used to find the acceleration. So let's actually take this situation. Let's get rid of a few things here. Let's clean this up a little bit. We'll get rid of this and delete that. Let's take this. I'm going to take this. I'm going to shrink this down and stick it in the corner here for reference. And let's actually take that situation and actually work through it, and we'll see how these things can actually be found and work together. So here's my strawberry and orange again. Let's get some values going here so we can actually find some stuff. So let's say we have an 18 kilogram strawberry. Let's say we've got a 12 kilogram orange. And let's say the coefficient of friction is 0.75 between the strawberry and the table. The orange doesn't have a coefficient of friction because it's not on a surface. Okay, so we're going to find the acceleration, but let's forget about that for now. Let's just start by just finding forces. Sometimes it's good just to find forces. So obviously both of these things have a force of gravity. So I can find the mg for my strawberry, and I can find my mg for my orange. So if I find the force of gravity for my strawberry, mass times 9.81, I can find out that my strawberry has a force of gravity of about 177 newtons. If I go to my orange and do the same type of thing, it's got a weight or force of gravity of about 118 newtons. All right, so let's see what these forces are actually doing. For my strawberry, that 177 is going straight down, causing the table to push straight up to keep from breaking through. So that force of gravity is actually creating the Fn between the strawberry and the table. So that is my actual Fn. So my Fn would be 177. Well, now that I have my Fn, I can use that to find out the friction between the strawberry and the table. So the coefficient is 0.75. If I multiply that by 177, I'll get a friction of about 133 newtons. So that's sort of what's going on with my strawberry. If I look at my orange and see what's going on with my orange, that 118 newtons is trying to move everything. So this is actually going to also be my applied force. That is how much force is trying to actually move it. If I cut the string, the strawberry wouldn't go anywhere. So the orange is the only thing actually supplying an applied force. And if the system was just sitting there and doing nothing, that would also be the tension in the string if it was just at rest. If it was accelerating, it'd be a little bit different, but for now, it would just, at rest, it would just be 118 newtons. All right, so let's see what we actually have going on here. If I try and sort of put everything together, if I look at how much is trying to move it, that's my applied force. I've got 118 newtons trying to move this thing. If I look how much is trying to slow it down, I've got friction at 133. I've got 133 trying to slow it down. Now, just with this alone, I've got a problem. I've only got 118 trying to move it, and friction is 133. Now, keep in mind that when you use this formula, it always calculates the maximum friction possible, which means I've actually got more friction than pulling force, which means this thing isn't going anywhere. So the net force would be 0, the acceleration would be 0. It's not going anywhere. In fact, this thing would be in static equilibrium. Okay, so the net force is 0, the acceleration is 0, everything's equaled out. Friction wouldn't actually be 133. Friction would actually just go up to 118, just enough to actually balance out the applied force, and it can go higher. So you need to pull with considerably more force than what we got in order to get this thing to move. So let's modify the situation a little bit here and get this thing to move. Let's add another orange. Okay, bit of fruit salad going on. There you go. So here we've added another orange. Now we've got more than enough force now in order to actually get this thing to move. All I've done really is adjusted my applied force. So instead of having just 118, now I've got twice as much orange going on, and we'll assume they're identical. So right now, my new applied force, or my total applied force now, is going to be twice this. So that is going to be 236 newtons trying to pull this thing down. Well, 236 is definitely more than 133, so this thing is definitely going to move, which means I can find my net force. So if I look at my net force, I've got 236 trying to move it. I've got 133 trying to slow it down, so I am going to subtract those two, and it gives me a net force of approximately 103 newtons. Now that I have my net force, I can find my acceleration because I have all my masses. So acceleration would be the net force divided by the mass, and you want to use the total mass because they're all tied together, they're all moving. So my net force would be 103. My 18, my 12, and a 12 gives me a total mass of 42 kilograms. And if I divide those two out, this system will accelerate at about 2.5 meters per second squared. And obviously it is going that way. Now, obviously, there's a whole bunch of stuff going on in this one question. There are forces all over the place and blah, 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 but we've got all the ones we mentioned. Like first, we found our forces of gravity. Our forces of gravity were used to find our applied force and our normal force. Our normal force was then used to find our friction. Our applied force and our force of friction then found our net force. And of course, we mentioned a little bit about tension. Now, the big thing about questions like this is just take it one thing at a time. Find one force, see what it can lead to. Find another force, see what it can lead to, and see if the forces can tie together somehow. It's all about little tiny things, little tiny forces, and sort of seeing how things piece together.